Thank you very much for the opportunity addressing you here in this conference. So especially thanks the organization of KiCAD to give me this opportunity. I used KiCAD because I was looking for a replacement for typing in net lists. Basically, you recognize it from SPICE, yes? I didn't want to type in net lists. So I needed to have a schematic capture program that gave me net lists. So I worked with LT-SPICE, with GSCAM, with Lepton EDA. And there were a lot of requirements like, oh, I want also to have SVG files to publish in my book. I want to have websites generated, nice pictures, etc. And that brought me to KiCAD. So that is the only link there is, basically. So let me tell you a little bit about what I'm going to tell you this afternoon. First, a little introduction. Who am I and what am I going to do here? Second, a little bit about analog design, because this is about analog design. Basically, it is about analog design automation without using AI. Symbolic analysis and analog design, how you can use it in analog design. Then about slide cap. I want to spend most of the time on an example that I prepared for you. And I hope there will be still enough time left for the questions from you, because let's say the material itself is so huge, I can only have a few snapshots for you. So there probably will be a lot of questions at the end. So after some work at Philips and other companies, I started as freelance designer in 1997 until now, mostly focused on design studies, proof of concepts, and I gave also training, on-the-job training for analog design engineers and in-company design courses, especially a method of structured electronic design developed in Delft. In the 80s, there was already someone who designed a program that could design amplifiers without AI. It was an expert system. Unfortunately, it was written in a language that got lost, that no one knows where it is anymore, no one can use it. And if a university finishes with some PhD research program, then usually they start a new one, and often it gets lost. But the material itself is extremely interesting, because I think it's a design approach to analog design based on systems engineering. And system engineering is a professional design approach for designing airplanes, designing rockets, etc. Everything you want to have reliable and safe. So, as I was giving courses, and maybe some of you studied analog electronics, and what you always needed to do was making tedious calculations. So I saw students making tedious calculations about anything, and then it was 5 pages long, and then on page 3 there's an error. And do you then have the guts to start again? Or do you jump to SPICE to try and roar? Well, unfortunately, it's easier to jump to SPICE and just try something. And it's still common practice that many people try something, because there's not enough support for the early part of the design process. So I thought you need some support for that. And let's first make a tool that does the calculation for you. And what kind of calculations do we do? I will come to that point later, because of course we cannot do all the calculations. So, but the basic question to be answered is, how do we go from the idea to a product? And if you look to an industrial way of working, you would say, well, you start by making a requirement specification and a test specification. And there are all kinds of issues in this topics in the specifications that you want to address. And, well, I'm not going to read this, you can download the sheets in a link, and you enter the product. I just made a picture of a product I had, so that I have no conflict with legal things, etc. So don't try to read it, it's not important. But the whole thing is what's in between. Where do we have as designers, as tools, to go from the idea to the product and test at the end if things still match? Well, what is the design motivation? What is the motivation for our design choices? What did we have as alternatives? One important thing in designing is, and I think in Delft, I know that industrial design teaches it, you should document non-selected design topics. Why? Because maybe you didn't select them because of a reason that is now valid, but not in 10 years. Technology can be changed, and then you can say, wow, we could have the other one. We have another way. So that's important. And I often, if I read design reports, I only see this is how it works, this is what I did, this is how it works, this is what I did. We are just not supported by software in having this whole path clear in front of us linked. And a design document is also for review. And the review is not, let's say, to let colleagues make nasty remarks about your design. But when a design review is there, the responsibility of the design goes from the individual to the team. That's the whole idea behind the review. And so a review is needs very good to be supported with documents and arguments. So, and what tools do we have then to do this all nowadays? What do we have for analog design? I cannot speak about digital. I know there's many more tools available for digital. This is much more structurized in digital design. But what tools do we have for analog? Well, pencil and paper. We have numeric and symbolic computer algebra systems like MATLAB or Maxima, Derive, name them all, and you can make formulas and drive something. We have numeric simulation, but yeah, numeric simulation is verification of the design. It's design verification. So how can I design with a verification tool? That can only be if I try something. And what do you try then? What is the basis for this trying? Schematic capture and PCB layout, and most horrible is, of course, that many people make them even in Word and PowerPoint. All their reports is not reusable. So if you want to support this whole process, you need to support from idea onto a report. And if I click on a specification and I change the specification and I will run all my scripts associated with design, I want to have everything updated. The bill of materials, the reports, the expressions, the tables in the formulas, and maybe even a warning that I changed this design, but there's a showstopper. It's not longer possible to make it with the selected topology. So, what do you have, and how do you do it? That's so. What is your path from idea to schematic? So. We now have ChatGPT, as you just type in, I want to have a transimpedance amplifier, bang, you get a schematic of a transimpedance amplifier, you build it, you go. Or you do it in Google. Yeah, you do it in Google. You say, okay, I want to have a transimpedance amplifier. You type it in, and here you have a lot of pictures. Or like me, maybe you see my clumsy handwriting. You just make some sketches and say, okay, this is, and I need to know this, and need to know this. Or we go to a combination of a thing that can help us. Python scripts with KiCAD as communication tool for schematic capture and ngSpice for verification at the end. So there's a lot of things included in what is called Symbolic Linear Circuit Analysis Program, written in Python. So I hope some of you know some Python, that's the easiest following of this topic. But if you don't, I just guide you through the arguments and why we do things and not especially how we do things. That's also important for this lecture. You can download stuff. There's a site from the university. You can download the program. You can read whatever you want. There's a huge help file. So, but what are we taught at school if we do analog electronics? We are taught, for example, to calculate the common mode reaction ratio of a differential pair without knowing why we do it. And then we have huge expressions. Or we are calculate what is the noise of this thing, while we don't have any requirements for the noise. So what do we need to do? Well, this analysis, you're trained in it. And this analysis can be automated. So that's basically what we do. It's an analysis program. You just put a schematic in, it builds a matrix, it puts your formulas, your expressions in the matrix, you do bang, and you have an expression. That's the simple thing. But the trick is, of course, what is the design question to be answered by this expression. And how do we find the answer? So that is what we call a design equation. A design equation is the inverse of an analysis result. In an analysis result, we write the signal to noise ratio is so and so much if this resistor is so and so much. And in design equation is the resistor is a function of the signal to noise ratio. And then you solve for the budget given for the signal to noise ratio, your resistor. So it requires analysis and solving. That's basically the whole idea. And that's why I'm so happy that that Symbolic Python, SymPy, is so strong at the moment that it can really solve a lot of type of equations. And now the trick for you is not to make such equations that try to solve 20 variables at one time. So we need to have, and that's the most important issue of structured electronic design, we need to have a sequence in which we are going to answer our questions. And the basic idea about systems engineering, I always use the comparison with building, with designing an airplane. You know, someone is designing the fuselage, someone doing the wings, someone doing the wheels and the lamps and the motors, and then we have all the functions. So eventually we started with what we call a functional decomposition. And this functional decomposition, these functions need to be assigned to objects. And this is the real physical world. And now we say this group here are going to make an object and you are going to make an object. But at the end, it should fit. That's what we call interfaces. So we have to define the interfaces. And another thing, of course, is that the wheels cannot be made for zero weight. So they need to have a budget. Because if the wheels are too heavy, the plane will never fly. So the whole thing is budgeting and functional decomposition. As much as you can orthogonalize it, you can do it. And if you apply it, for example, for an amplifier, you say, if I make a feedback voltage amplifier, we did it this morning with the workshop about ngSpice, then you have a question like, well, what should be the signal to noise ratio? What should be the bandwidth? What should be all this stuff? And how do we define our circuit parameters given those things? Now look at the feedback amplifier. You have a controller, which we call op-amp in our daily work, but the function is it's just a controller, and you have a feedback network. They both contribute noise. So if you want to design them independently, you have to give them a budget. So if my amplifier should have a budget of 3 dB for noise figure, I say, okay, let's do 1 dB for the feedback network and 2 dB for the controller. And of course, the budgeting is always based on experience. A novice can never assign real budgets. You need to have experience like, well, this is a nonsense budget, you know, putting 0.1 dB there is like, it's a showstopper immediately. So, of course, you need to have some experience. And that is what you maybe can get from AI. That could be a nice interface. What are reasonable numbers? So the trick is, we need to set up design equation for several performance aspects. Now, we are focusing mostly on amplifiers because amplifier is really a basic function. So, where is always relevant for an amplifier? Well, we take the Shannon. Yeah, Shannon is channel capacity, bits per second. So it's bandwidth, noise, and power you can get through it. That if that is lacking in the specs, you cannot make an amplifier because you don't know what you are doing. So we need to have models for small signal. Small signal analysis is SPICE called, unfortunately, AC analysis because it also holds for DC. So small signal analysis. For unpredictable errors. Unfortunately, in SPICE, most macromodels of operational amplifiers have their offset of the op-amp as a fixed voltage source, which is useless. Because the standard deviation is known, but the mean value not. Yeah, it can be 0, but it's all about standard deviation. So we need to have, for example, we need to have a design equation. What should be the standard deviation of the offset of my op-amp so that my voltage range at the output of the transimpedance amplifier is within spec? That's a design question. So we need to have that also. What should be the equivalent input noise sources of my op-amp so that the total noise at the output of my system is in spec, even after some weighting function, DIN A, correlated double sampling, whatever you want. That are design questions, and they can all be solved with the current version of SlideCAD. But you do it yourself. I don't have a program in which you put your specs, you push a button, and there's a schematic. No, that's not that far yet. You need to know, you need to set up your own models. And I want to show you how it works in an example consisting of 7 Jupyter notebooks. Oops. And it's a transimpedance amplifier. And each notebook addresses one design question with a simple but sufficient model. And if I give lectures at the university, I always say these 2 quotes that are there in very small letters. Other models are wrong, but some are useful. That's one. Second is, models should be as simple as possible, but not simpler. I have seen people that use Symbolic simulator to say, oh, I have a circuit, let's make everything symbolically and then calculate the transfer. Well, and what's the use of that? What you going to do with that? Look at it and say it's beautiful, it's 20 meters long. So we need to have a design question. We need to have a model that exactly addresses that design question, doesn't do much more because then the model is too complex, and not less. So what we're going to do here, you see a few the steps through the design. First, I will show you how to store specifications in a simple CSV file. In the future, it will probably be a database, but I really need to work together with software engineers because I'm an analog designer and I program like this in Python. Yes, you can imagine how it looks if you open the code, but it works. So I want to create a community working on it and using it and making it better. Then we go to the feedback concept. So here we just have the question, what are the specifications that we want to have? Then we go to the feedback concept, and the feedback concept we ask, what should be the feedback network considering the transfer and the noise? So then we go to 2 steps in which we are going to define the budgets for the controller. So that's basically the hierarchy that is in it. Yes, so the controller, the op-amp. And why is it 2 steps? Well, there are 2 different things. If you use feedback, you can improve some errors and some not. If your op-amp cannot drive the load, you can make more loop gain, but it will never be able to drive the load. If your op-amp has too much noise, you can make more loop gain, but the noise will always be limited. If the offset variation of the temperature is too much, you can increase the loop gain. Loop gain means more feedback, but it will never be better. That's what you need to know. So that's why we have first group, things that cannot be affected by negative feedback. They'll generate showstoppers. Design is risk management. Basically, the process of designing is like the biggest risk first. Because if at the end of the line, so we do, let's say we want to make this airplane and everything fits and the last screw in the wheel doesn't fit, then it doesn't fly. And that's a waste. So it's always the devil is in the details, in the last details. So we have to be sure that we address that. So that is called top-down design with bottom-up awareness. So you need to know your technology, otherwise you cannot do it. And you need to know about showstoppers. So here you see, I have noise, accuracy and temperature stability, power dissipation and drive capability, things set by the budget already taken by the feedback network and budget that cannot be improved with negative feedback. The second group is what shall be the, let's say I want to have this pin diode amplifier, this transimpedance amplifier to have a bandwidth. I stated like 500 kilohertz, just do something, yes, it's just an example. What should be the bandwidth of the op-amp? the gain bandwidth product, because that's the selection criteria. What I want to do from these two steps, number 3 and number 4, is end up with a list and say, this must be smaller than this must be larger than this must be smaller than this, blah, 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 blah. Put it in a search on the database, and it gives me 10 op-amp types that are available. And then I can maybe make a selection based on the price or layout or other issues, and then run ngSpice and see if it's working. If ngSpice has good, that's not ngSpice, if the manufacturer provided correct models, because that's often an issue. So then, if we have selected the op-amp, we designed already the noise, we designed already the bandwidth, you hardly have to check it. If you do your work correct, it will be correct. But we didn't do anything about the frequency characteristic. With negative feedback, we always have the risk in making oscillators instead of amplifiers. So we need to design the frequency response. But you are not going to design the frequency response if the bandwidth is not okay. That's why we first do the bandwidth. So we first need to have an op-amp. Then we know its gain bandwidth product, we know the input capacitance, etc. And then we can say, what is the frequency compensating needed to get a nice response? Okay, that's why it's here. And then, of course, there can be many more steps, but for this presentation, I only have, then we do numeric verification with SPICE. So let's go to the example. You can interrupt me if you want. So maybe I do this first. I say a view. What was it? No, what was it? I clear all up. Where is it? Edit. Clear all output. So you see the steps. The specifications. For the specifications, I need to have a functional model because the specifications relate to something. They're not just, out of the air. They need to be defined somehow. So I need to have a functional model. Then I go to the feedback concept of the amplifier. Then I do op-amp budgets 1, what I told you. Then I do object budget 2, which is then mostly the gain bandwidth product. Then we are going to select the op-amp. There's only one here to select. So, it's a very... But I can jump into, depending on your question, I can jump into the other scripts, because all these steps import another notebook. And in this notebook, I do the job. So we can always jump into something. And then we'll do the ngSpice verification. So the whole idea is that, you go, that's why everything, I always want to have it in batch. So unfortunately, with building, for example, ngSpice in KiCAD, I have to sit behind the terminal. I cannot be in the bar. And here I want to press a button, go with my friends to the bar, come home, and the amplifier is finished. That's the whole idea of design automation, not sitting behind the screen and do half of it yourself. So let's do run all cells. And let's hope that in the demonstration it also works. So it imports the notebooks. And here is the final schematic with back annotated operating point information in it, run by ngSpice, and the magnitude and the step response of the thing I designed. Now you could always say, well, you're just faking something, but let's jump into it a little bit. Then you can really see what we are doing. So here, probably I have some 4.5 volt output step. I have about, what is it, like 600-700 kilohertz bandwidth. And this is the circuit. I have 3.2 millivolt offset. Let's go to specifications and change the spec. And then first run it again with new specs. And then maybe we can do it interactively, that you have questions like, oh, how do you do that? How can you illustrate that? Or we go one by one through the notebooks. That's all possible. We have some time left, isn't it? Yeah. So let's go to the specifications first. So I have a notebook here, specifications, that is called by this one. transimpedance specifications. Here you see what I do. I have an amplifier concept, and the concept is that a current from the pin diode, which is modeled as a current source, a signal source, in parallel with the diode capacitance, and since it is in reverse bias, I don't need anything else on this. For the signal, this is enough. There's noise of the source specified. There's also the power, the optical power, and the gain of the diode is specified. So I just have here the value of the peak value of this source is equal to the product of the gain and the optical power I put in it. There is a dark current, that's a DC current, and this DC variance is at the moment 0. But I told you there's a simulation mode in which we can find expressions for the variance of voltage sources, resistors, etc. So in order to get budgets for offsets and tolerances of resistors, for example. So here this current is sensed in a voltage source. The positive current direction is a voltage source is from plus to minus through the source. So it means if I want to have a positive voltage here out, that I need the current is flowing in this direction, that I need to have an inversion. And since the amplifier converts current into voltage, the units will be R. So this has nothing to do with some resistor in the circuit yet. This is just a model, the desired gain of the amplifier. And in this stage, if I have the output swing I want, and I have the input peak current I can define with this circuit already the gain that I want from my amplifier. So that's basically done in the specs. So here you see all the specs. Here the output voltage, the voltage here at the output, so I call it V load, not V out, V load. I take the full scale ADC voltage that I want minus some headroom for errors. That's a budget. So this V headroom for errors, you see? It's in the spec. If I change it later, I will change it later and you see the curve changing because it can be more voltage or less. For the noise, I want to have a system of 16 effective number of bits. That means that the RMS value of the noise at the output over the frequency range of interest is equal to 1 LSB. And at 1 LSB I know because I know the ADC voltage range and I know what the output voltage range and I know what LSB is, so that's okay. So here, this is maybe some students found it a very clumsy way of doing, but it's the only way I have. So there will be probably a shell around defining it in a nicer way. But here you define a spec item, which is for a parameter, a description, a value, units, and a type. So this is the source and the load is interface specification. But the resistor that we want, and this is the load is also interface. But the resistor is design here. The resistor RT, that's a design thing that is in the table. It will be in a table of design specifications, and all other things are performance specifications. So I make the specifications. They will stored in a CSV file. I import them, assign them to the circuit, and I can really in a nice table. That's all done for you, all this formatting. I can see how they are symbolically defined and what is the numeric value. So here we have this resistor is 163.6 kilo ohm. The number of digits you can set in an INI file. And then, yeah, that's basically it. And I can also display that's what I do later here. Here you display the specifications in a nice readable way. And this is why you don't need PowerPoint anymore, yes? You don't, if you want to have a management presentation, you just make a notebook and you present it and everything is connected to your design work. Reusability is, let's say, the holy grail. If you do something 2 times, and you have to edit your formula because something changed in Word or in PowerPoint or whatever, you create errors. So everything should be connected. So that's what we do here. So let's make it a little bit. Was it too small? Is this good enough? So here you see a list of specifications. And what I can do now is I know that this resistor, that I calculated should match the required output voltage swing to the input current, and I can just check that at the end and see if it's okay. So that is, so if you run this notebook, run all cells, then it creates a table, what we have put and what we have seen here. That's all. There's nothing much, but this table is stored and used by the next step. And the next step, what I was doing was changing the specs, yes? So I was changing the specs. So let's say I'm going to change the specs to, where it is. Let's make the headroom for the ADC 1 volt instead of 0.5 volt. And let's make the dark current 200 nanoamps instead of 20. Then I want to see in my ngSpice simulation at the end, 4 volt output and my offset. So I'll save. And of course I need to go to example now and run the whole thing here. Run all cells. And we pray again that it will work. Failed. Now where's the circuit? Was it somewhere here? 10 times row offset. So everything is connected. And also, but you didn't check that maybe, the feedback capacitor for the frequency compensation is changed. Because it calculates the frequency, and the gain is changed, the resistor was changed. Maybe the gain bandwidth product or the pole positions were different. It needed to have another compensation. It calculates another compensation, puts it in. So basically that's the presentation. Well, let's finish the presentation, then I go to the questions, because I'm guessing you might have some questions. Yeah. So this is the presentation. So we did this all in one step. So very simple thing about what you see here on the PCB is an analog class AB amplifier having plus or minus 1000 volts output, putting it on 2 microfarads with a butterworth free flat bandwidth, and it has optical isolation between the input stage and the output stage and overall feedback. So we have about 3 transimpedance amplifiers in it. We have a loop integrator in it, and overall feedback and frequency compensation, and we have discrete MOSFETs, etc., everything in it. And I couldn't have done this design without SlideCap. It would have been too much hand calculations. So, but of course, you need to know a lot about this design methodology, of course, also to appreciate it very much. But I hope this inspires you to use it. Here you find your information. SlideCap.org is the help file behind SlideCap. So if you do click this, you have the manual. And the manual is also generated with itself. So all the examples are just Python scripts, and they generate expressions. And a new version of my book, I also want to make it this way. The old version, I had to import HTML output pages, convert them into SVG. It's all a headache. So now everything is automatic. So it's like this. You make a LaTeX document, or you make a Sphinx website. For the Sphinx website, you type RST. For LaTeX, you type LaTeX. SlideCap generates snippets in RST or LaTeX for complete tables, expressions, whatever you want. And you just include them. So you run, before you compile your LaTeX document, you run SlideCap, then you compile your LaTeX document, everything up to date. And if you compile your website with Sphinx, you can do it in the same way. So your documentation is always linked to your specs. That's the whole idea. And your motivation of the design is there in all your scripts. So this was the website of the thing. This is the website of me, so it's not so interesting. This is KiCAD, you know yourself. There's also an interesting website, but you can find it through my website of the University of this structured analog design, which is a method which is, I think, unique in the world. So we're the only one facing on the process of design rather than on the results. So let's stop here and then ask for questions. Is there time left for questions? Okay. Questions? Oh, it was too difficult. No questions.
I can start with one if there's no others. So yeah, looking at this, like the first thing that comes to my mind is like loop compensation for power supplies, for switching power supplies.
Also, yeah.
Yeah. Do you have an example for that?
Not really, let's say that I can show it, because many stuff I have is related to customers. But usually what you do is you make a small signal equivalent circuit of your power supply, and there's also root local techniques included. And one of the strong points of SlideCap is it doesn't give you any false poles and zeros. It calculates with integers, and it uses the most horrible method, which is very good for Symbolic, for the calculation of the determinant of matrices, which is just Laplace expansion, but it's still fast. But yes, you can do this for this as well. We do it for chip design, for noise, for selecting MOSFETs. There's a book that relates, for example, the geometry and the operating conditions of a MOSFET with two small signal parameters. So you design here, you say, okay, I want to have an operating current optimized for noise. You find out, or you can really equate this out, and then find the operating current, the geometry, and then switch to BSIM model. And so basically I use EKV, and then you switch to BSIM, and it's within 5%. So yeah, it's huge. Yeah.
This is really impressive. And my question is, have you done this all of yourself, or are there other contributors?
No, this is my work. But I'm 72 years, I worked a few years on it. It was my first Python program. Yeah, you need to have a challenge. As if you could start programming, you need to have a challenge. So, yeah.
So I saw you showed the specification sheet. You had there a model for an op-amp. And
so the selection of the op-amp?
No, you had in your specification sheet, in your specification notebook.
Yeah.
You had this model of your op-amp.
No. In the specifications, I had a functional model of the circuit.
Functional model of the circuit.
This is not at all representing an op-amp.
All right. And then in your example, you had the circuit there that came out, basically. Yeah, this one. Did you draw this circuit beforehand, or did...
No, so the program is not yet capable of drawing circuits. I really would like to have, but it's very difficult. I didn't see really. Well, I think there will be efforts in it, like generating. I want to generate from the matrix a circuit, and then draw it in a schematic tool.
So my next question is, basically you have drawn this circuit and you have parametrized it by basically having this CSCF.
That is like the op-amp, yeah. So the op-amp here, internally, SlideCap uses models, yes. So SlideCap just uses sub-circuits. So you can nest sub-circuits infinitely. So let's go to where it was. SlideCap. Just a little bit about the web. And then, for example, the netlist syntax, devices and built-in models. and then you go to operational amplifier, and then you see here, what is the operational amplifier? So this is the model of the operational amplifier. It consists of a voltage controlled voltage source. It has the common mode and the differential mode input impedance, and it has some output impedance. And the voltage controlled voltage source can be given a Laplace transfer, and the output impedance can also be given a Laplace transfer. And that's what you do. So for the OPA 627, I put in there a Laplace transfer having one. Well, in this case, it was a very simple one. Let's go to the expression. I think it is in gain bandwidth product design. Because where it was op-amp purchase 2. So here you see the voltage gain of the op-amp. This is the DC gain divided by 1 plus S times the DC gain divided by 2 pi, the gain bandwidth product. So it's a single pole op-amp. And that model is in. And it has also this fixed resistive output impedance, because that's in the data sheet. Well, that's not in the that's the simplest model I want to have at that moment. And differential and a common mode input capacitance. And there's variables then at the end turn out to be, let's say this is the loop gain expression, something you shouldn't look at. Yeah, that is calculated from the matrix. Yeah, you can make it like this if you want, but this is the background. Here there's a function, give me the coefficients of the differential equations, here they are. And the bandwidth of a system of which all poles are dominant is given by the coefficients of the denominator with the highest order of S. So you take this coefficient together with the DC gain, and you have the requirement for the bandwidth. And here you see, I just solved this. Here you see the solve that I told about. And here the result is gain bandwidth is a function of, yeah, of course, if you put more capacitance in it, you need to have more gain bandwidth for it to compensate for that. So I can select an op-amp now, having all the parameters like CC, CD, and RO in it, and say, okay, if you have this input stuff, what should be then the minimum gain bandwidth product I need from you to have my transimpedance amplifier 500 kilohertz?
Yeah, with the performance that you...
Yeah. And the models are behind the circuit there. Does it elucidate a little bit?
Yeah, a little bit. Very impressive.
Thank you for the presentation. Just curious, how long does it take to run the complex model like the board you showed at the end?
Sorry?
How long does it take to run the complex model of the board that you showed at the end?
Well, you saw it happening, yes?
Sorry?
You saw it happening.
But it was only for one op-amp. But if you have the complex model of the
presentation. I have the most complex circuit I have was designed by a customer, and he wanted to do something that you shouldn't do with SlideCap. That is like verification at the end. I think verification, you just take ANC splice because it's faster. You're not interested anymore in the equation, but just in the result. But if you want, you can do it. So I had a 52 by 52 matrix with S in it. And the matrix calculation takes 3 seconds.
Okay.
Which is extremely fast for such a symbolic thing. So, so I have also some more complex circuits, but usually within 100 seconds or so, you have a quite complex circuit done.
Okay. Thank you.
Okay.
So for how many unknowns can your system solve?
Sorry?
So for how many unknown variables can your system solve?
Now that's limited by SymPy. The algebra system behind it is SymPy. So if SymPy can solve it, it will solve it. But the question is, can you define your problem so compact as possible? That's the challenge, yeah. let's say, take a, we have an example now running in Delft for the masterclass of this course, which is a low noise amplifier, chip amplifier with dual loop feedback. So then you have 2 loops of feedback making a nicely low noise defined input impedance, for example. And then you have requirements for the gain, for the input impedance, and for the noise. The gain should be exact, the input impedance should be exact, and the noise should be better than. So I need 3 models. One models give me a symbolic expression for the input impedance as a function of the feedback elements, which are resistors. The second one gives me a symbolic expression for the gain as a function of the resistors. And the third one gives me a function of the noise as a function of the resistors. And I solve them concurrently. It's within a flash. And it says the resistor should be, one resistor or whatever should be smaller. This one should be so large, this so large, and this should be smaller than that. So yeah, you can, but you shouldn't solve 6 things in a nonlinear equation concurrently. Yes, it's horrible. You can only ask what you, otherwise you go to, this is the opposite to sensitivity analysis. You could do this in SPICE. What can you do then? Change the parameter and see what happens at the output, and that's called sensitivity analysis. But then you hope you change the right thing. You don't have an analytical expression. This works with analytical expressions.
I have the question, have you this example also on your webpage that
If you
can show this?
If you go to the presentation, where's, oh, I clicked it away, not. Oh no, I was here, it was the presentation. If you go to the presentation and you go to here, click.
Can you zoom this?
If you, there you go, this is like you click on this title, example, then you download the sources, the Jupyter Notebook sources. Of course, you have to install KiCAD and GSpice, SlideCap 12, and Slide, yeah. But you can run this. It's all available.
Okay, thank you.
Everything is open to the world. More? Okay. Thank you.